Let's start with an idea that surfaces exert forces. It's not a new idea. It's a hypothesis, a successful hypothesis that explains many of the things that liquids do. I can demonstrate these forces by catching a soap film on a wire frame. The fact that the tension in the film is uniform in all directions explains the circular arc of the thread. To enlarge the film, I must do work. Force times distance. Pulling down the thread increases the area, takes energy to pull more molecules up into the surface. Another example of the pull of surfaces is given by a loop of thread placed on water. Soap molecules lower the surface tension of water. The higher pull of the outer surface pulls the loop into a circle. The old camphor boats operate on the same principle. Where the camphor touches the water, the surface tension is reduced, and the higher surface tension on the bow pulls the boat forward. Particles of camphor scraped onto a water surface will also move. The camphor dissolves unevenly around the edges. In this film, we shall examine the effects of these surface forces on the shapes and the motions of liquids. The angles at which surfaces intersect are determined by the pull of surfaces. If three soap films meet, they must meet symmetrically in order for the pull of the surfaces to balance. The angles are all equal, all of 120 degrees. More than three films cannot intersect, except momentarily. You can see that four films meeting are unstable. A more complicated circumstance occurs where solids and liquids meet. With drops of water on wax, the water, the wax, and the air clearly do not occupy the same angles. It is not so readily apparent that solid surfaces exert a pull. Instead, it is more useful here to consider surface energies. Just as it took work to pull out a liquid surface, it takes work to create a solid surface. The contact angle is that which leads to the minimum available energy of the system. Here is mercury on glass. Notice that the mercury angle is larger than 90 degrees. If the liquid angle is larger than 90 degrees, we say that the liquid does not wet the solid. With a drop of water on a bar of soap, you see that the liquid angle is less than 90 degrees. The water wets the soap. If we accept this hypothesis that surfaces exert forces, we find that there are three boundary conditions expressing these forces that need to be used with the continuum equations of fluid mechanics. We've just seen examples of the first, that where surfaces meet, the contact angle is uniquely determined by the energies of the interfaces. The second boundary condition comes from a force balance across surfaces. One finds that a curved liquid surface has a higher pressure on the concave side. For example, the higher pressure inside forces the smoke out. The energy of the surface becomes converted to the kinetic energy of the smoke jet. We can calculate this higher pressure. Consider the upper half of a gas bubble immersed in a liquid. Surface tension will pull down all around the equator with a total force equaling the surface tension expressed as force per unit length times the length of the circumference. That must be balanced by an upward force, the pressure difference, times the area at the equator. This simplifies to the pressure difference equaling twice the surface tension divided by the radius of the bubble. A soap bubble, because it has both an inner and an outer surface, would have a pressure difference twice as large. The spherical case is a special case of the more general equation that involves the two radii of curvature necessary to specify curvature of a surface. A spherical bubble has these two radii equal. This equation also indicates that the pressure inside small bubbles must be large. It suggests that an infinite pressure difference would be required to generate new bubbles. And it is, in fact, very difficult to make new bubbles. We apparently see many being generated in boiling water, for example. These, and practically all of the bubbles you will ever see, are not new. They are pinched-off enlargements of other bubbles, usually of vapor pockets in cracks where liquid has never completely penetrated. This glass beaker was carefully cleaned. It contains very little dirt with cracks to act as bubble sources. If we pinch a small glass tube to create a gas-filled cavity, and then bring this rod down into the layer of superheated water, we find that it acts as a nucleation site, that it can generate any number of new bubbles. The vapor cavity never completely disappears. A small amount always remains ready to act as a new nucleation site. Actually, it is possible to make new bubbles in a liquid, but you won't do it by normal boiling. Water carefully cleared of all bubbles can withstand a tensile stress of over 5,000 pounds per square inch. Water molecules attract each other so strongly that it takes at least that much tension to pull them apart. When a liquid contains a large amount of dissolved gas, such as carbon dioxide, it comes out as bubbles. It comes out wherever there are nucleation sites that provide a surface across which the molecules can pass into vapor spaces. It may appear that this liquid does not contain much dissolved gas. We can check that by introducing the roughened end of a glass rod. You see that there is a lot of dissolved carbon dioxide in the liquid, only waiting for nucleation sites to come out as bubbles. The water in this faucet is being held up against gravity by surface tension. Notice that the curvature is sharper at the bottom of the drop to withstand the higher hydrostatic pressure there. When the weight of the drop gets too large for the upward pull of surface tension around the drop, it falls. If these drops had been alcohol with its lower surface tension, they would not have been so big. One of these burettes is filled with water, one with alcohol. The alcohol, with its lower surface tension, comes out as smaller drops. Another way of showing that water has a much higher surface tension than alcohol is to dip glass tubes into water and alcohol. Both liquids wet the glass, so each upper surface, or meniscus, is curved upwards. The liquid therefore rises until the pressure difference causes the alcohol, even though it is heavier. When a liquid wets a solid that has holes or crevices in it, it will be sucked in more and more strongly as the crevices get smaller and smaller. We can see this with two glass plates. touching on one side, but slightly separated on the other by a paper clip. The water rises between the plates, in this case into a hyperbolic curve, higher where the plates are closer. If a crevice is small enough, capillary action can raise liquids hundreds of feet high. On the other hand, if a liquid doesn't wet a solid, it tends not to enter holes. This is the principle of waterproofing cloth. All such capillary actions can be explained in terms of the two boundary conditions, the contact angles made by the liquid with the solid, and the pressure differences caused by the curved interfaces. Surface forces and the pressures they cause are the controlling factor in the breakup of jets and sheets of liquid. A cylinder of liquid, like this, will always break up into drops. The cylinder will be slightly uneven, and where it is smaller, the radius of curvature will be less, and the pressure higher. This higher pressure pushes liquid up and down into the larger, lower pressure, fatter region. What was small becomes smaller, and the cylinder pinches off into a set of drops. This occurs so rapidly that you cannot see it clearly by eye, but in slow motion, slowed down 200 times, one can see the initial disturbances amplifying. Lord Rayleigh calculated the speed at which these disturbances would grow, and he found that for a disturbance wavelength of about 4.5 times the diameter of the jet, the disturbance would grow most rapidly. This is about what one sees happening. Surface tension also causes the rupture of sheets of liquid. This soap film, being shown in slow motion, slowed down 300 times, will be touched by a pencil that has been dipped in alcohol. A liquid film can become thinner by stretching or by evaporation. If its thickness reduces to a distance of the order of magnitude of the distance between molecules, then a hole may appear. Once a hole appears, then surface tension will pull the edge along, in effect gobbling up the film. The pulling force of the film, twice the surface tension, is balanced by the momentum flux of the liquid entering the rolled-up edge. The velocity is high. The edge of a film about 1/1000th of an inch thick would zip across a room in less than a second. Another jet breaking up into drops is shown here, where a water jet falls on the end of this metal cylinder. In slow motion, the breakup shows more clearly. The rolling up edge advances into the sheet of liquid, advancing faster where the sheet is thinner. Drops are produced by breakup like this in many things, from fuel nozzles to lawn sprinklers. When the cylinder is moved, the sheet will take on many different forms. It can even bend back sharply upon itself, apparently violating conservation of momentum. If you think about it, however, the sheet couldn't go out beyond the radius where the surface tension is equaled by the radial momentum flux of the liquid. It is at that radius that the water changes direction sharply. For some time, we've talked about phenomena that involve the pressure difference caused by curved interfaces. Here's a beautiful example showing many of these phenomena. A drop of milk that in slow motion will hit a thin layer of water. The drop spreads sideways, and its impingement on the static water sends up a liquid sheet. The rolling up edge of this sheet is unstable and forms a coronet, which is pulled down by surface tension. Part of this liquid moves inwards where it meets to form a spike. The spike in turn is pulled down by surface tension. Surface forces lead to a third boundary condition that should be used with the equations of fluid mechanics. If the surface tension varies along a surface, then the surface must move. Consider a boundary between a liquid A and another fluid, such as a gas B. Think of a unit length of the boundary and the forces acting on it. It will be pulled in this direction by surface tension, and it may be pulled in the other direction by a slightly larger surface tension. If it is, then the surface will move, and it will move in that direction, carrying the boundary fluid with it. It will move at such a velocity that the shear force it exerts on the liquid and the shear force it exerts on the gas will just equal the added surface tension. That is, the variation of surface tension along a surface is balanced by shear forces in the bounding material. The gradient of the surface tension will be equaled by these shear forces. There are three things that cause variation of surface tension: the kinds of molecules that get into surfaces, the electrical conditions at the surfaces, and the temperature of the surfaces. For example, ether molecules lower the surface tension of water. If I take a solid block and spread a thin layer of water upon it and let ether molecules fall on the water, the surface continually moves away. Through viscosity, it drags the underlying water along with it until eventually it leaves the bare spot. A drop of alcohol also lowers the surface tension and very quickly causes a bare spot. This surface tension pumping action shows up well with a dyed mixture of alcohol and water. Swirling the mixture around the glass leaves a thin film on the side. Evaporation of alcohol from that film causes it to have a lower proportion of alcohol and therefore a higher surface tension than the deep liquid in the bottom of the glass. The surface continually moves up to the high surface tension region, dragging liquid up with it. It will keep pumping like this indefinitely, but since the liquid that is pumped up has no place to go, it accumulates at the top of the film, accumulates so much that it forms into drops that roll down, drops that are called wine tears. Notice that the drops have difficulty getting back into the deep liquid. Perhaps you can figure out why, remembering that they have less alcohol in them than the bulk liquid. Electrical charges, as well as kinds of molecules at a surface, affect the magnitude of surface tension. Electrical charges usually concentrate at surfaces where their repulsive forces on each other subtract from the surface tension. Mercury in dilute sulfuric acid with a bit of potassium dichromate added will form a chemical battery if another metal, an iron nail, is brought in as a second electrode. When the two metals touch, the battery is short-circuited and the charge density on the mercury surface is reduced. The mercury drop pulls up due to increased surface tension. With just the right position for the nail, the mercury will set itself into oscillation, repeatedly short-circuiting the electrical charges that build up when the mercury is not touching the nail. Mercury in nitric rather than sulfuric acid, again with potassium dichromate added, provides this example of surface tension variation. The electrical and chemical effects at the surface lead to surface motions that cause the mercury to swim toward the potassium dichromate crystals. The third way to vary surface tension is to vary the temperature of the surface. Increasing the temperature always lowers surface tension of a liquid. It becomes easier to pull molecules up into the surface. Heating this metal plate warms the liquid above, reducing the surface tension there. The warmer surface is pulled away, dragging some liquid with it. The opposite happens with an ice cube. Liquid above becomes cold, has a higher surface tension, so nearby liquid is pulled into the cold regions, causing humps rather than depressions. Now let's imagine what should happen to a gas bubble immersed in a liquid when the liquid has a temperature gradient. When, for example, the liquid is hot there and cold here. The cold side of the bubble will have a higher surface tension than the warm side. It will therefore pull surface around from the warm side. Surface will be generated here, flow around the bubble, and disappear at the cold end. This movement of surface with the viscous drag upon the boundary fluid will pick up a sheath of liquid and jet it off the back end. By jetting liquid this way, the bubble propels itself that way. It will swim up the temperature gradient, always moving to the hot region. Here we have a bubble. It moves to any hot region. If you wonder about the thermodynamics of this self-propelling bubble, wherever surface is created, heat is absorbed, and wherever surface is destroyed, heat is given off. Therefore, this bubble is absorbing heat at its hot end and rejecting heat at its cold end. It is a self-propelling heat engine. Here is a related experiment involving bubbles that can easily be done in the kitchen. Place an ice cube on a metal surface. It will turn around and around in its pool of melted water and perhaps stop and then move back and forth. This motion is caused by bubbles that attach themselves to the metal under the ice. Any motion of the ice causes a temperature difference over the bubble, and each bubble, through surface tension variation, acts to push the ice above it in the way that it was already going. If you try this, use homemade ice cubes, the kind that have bubbles in them. Swimming bubbles can also occur on a heated wire in a mixture such as acetone and water. At low rates of heating, bubbles of acetone and water vapor are generated at nucleation sites on the wire, but instead of rising off the wire, they will swim along the wire in a stately parade. Notice the jets of hot liquid that the bubbles project backwards. A moving bubble surface drags hot liquid backwards and jets it away from the cold end. The velocity of those jets suggests that the bubble surface is moving quite fast, about 1,000 bubble diameters a second. That is part of the explanation of why they move along the wire. Once they start moving, the wire is colder where they have been and hotter where they are going, so they just keep going to where it is hotter. An interface is more than just a geometric boundary. It exerts forces, forces which are sometimes important in large-scale systems, such as in space where gravity is weak. But more typically, surface forces are important in small-scale phenomena where the surface-to-volume ratio is high, as in most of the examples we've been looking at. Using the idea of surface forces, these phenomena can be understood.